My name is Geir Moe, and I am a metallurgical engineer with 30 years of experience in the application of stainless steels. I am a consultant with the Nickel Institute, which is the global association of the world's leading primary nickel producers. The Nickel Institute's mission is to promote and support the use of nickel-containing materials such as stainless steels and nickel alloys in appropriate applications such as food, dairy, and beverage processing and pharmaceutical production. Approximately 70% of annual nickel production is used in the manufacture of stainless steel, and of which about 20% is used in the fabrication of food processing equipment. General requirements for the fabrication of sanitary equipment intended for processing milk, milk products, food ingredients, beverages, or other edible materials is defined by the 3A Sanitary Standard for General Requirements. Stainless steels are the primary materials used in the fabrication of sanitary equipment because of their corrosion resistance to food products and the cleaning solutions used to ensure the equipment is sanitized prior to use. Acceptable grades of stainless steel are identified in the 3A requirements. Also, the fabrication of stainless steel equipment requires welding, which, if performed poorly, can compromise the corrosion resistance and cleanability of sanitary equipment. In order to ensure the highest quality of welding, the D18 Committee of Welding in Sanitary Applications of the American Welding Society has created specifications describing acceptable welding practices for the welding of tube and pipe systems and tanks and other equipment for sanitary service. To be able to produce a hygienic weld, a welder or welding operator must be qualified by standard test in accordance with AWS B2.1. In the United States, welder or welding operator qualification is achieved primarily by training, testing, and certification by the fabricator. The performance qualification shall be documented in any convenient format, provided all the test results and welding variables are recorded. A welder or welding operator must requalify when he or she has not welded with a specific process for a period of 6 months or more, or when there is specific reason to question the ability of an individual to produce welds meeting the requirements of AWS D18. Ensuring the purity of welding gases is paramount to producing stainless steel welds with optimal corrosion resistance by minimizing or eliminating weld discoloration. Excessive weld discoloration reduces resistance to localized corrosion in the heat-affected zone of a stainless steel weld. Oxygen present in air is the contaminating gas which causes weld discoloration. The nitrogen in air is inert and does not produce any discoloration. During welding, the hot stainless steel surface reacts with oxygen in air, producing a non-protective high-temperature oxide. In order to minimize weld discoloration during TIG and MIG welding, an inert welding gas, typically pure argon, is used to displace air and thus oxygen. When welding a tube or pipe, weld discoloration on the exterior is accessible and easy to remove. However, the interior of the tube is not accessible and large volumes of inert welding gas are required to displace the air. Effectively displacing air can be a challenge, but it is necessary to maintain corrosion resistance in the weld zone. The American Welding Society has produced a visual guide identified as D18.2. which displays a range of weld discoloration that results from various amounts of oxygen contamination. For sanitary service, a discoloration level of 3, produced by only 50 ppm oxygen or lower, is considered acceptable. In order to achieve this low level of discoloration, the purity of the gas is essential. Before the weld can be started, a sufficient purge time must elapse, allowing the gas to remove air from the tube. Even moisture present in the gas can contribute to the creation of discoloration, and thus the supply lines providing the inert gas must be leak-free to prevent drawing in air and moisture from the surroundings. Orbital welding is an automated machine welding process in comparison to manual welding. Orbital welding has almost exclusively been carried out by the tungsten inert gas technique, with and without the use of filler wire. AWS D18.1, which is the specification for welding of austenitic stainless steel tube and pipe systems in sanitary application, defines an orbital weld as automatic or mechanized welding of tube or pipe in which a welding arc rotates around a stationary weld joint. In comparison to manual TIG welding of stainless steel tube, orbital welding is achieved with a specialized orbital welding head, which incorporates a clamping device, TIG electrode on an orbital travel device, and a shielding gas chamber. In many cases, a manual weld can look as good as an orbital weld. However, an orbital welding setup can achieve an ideal weld profile consistently with almost complete elimination of weld discoloration. A consistent and preferred weld bead profile ensures easy cleanability of the tubing, and the very low level of weld discoloration ensures that the heat affected zone on the ID of the tubing will pass the weld discoloration acceptance criteria of AWS D18.1 and thus ensure optimum corrosion resistance is achieved. Welding is a fabrication process that joins metals by using high heat to melt metals in the area where they will be joined. The melted portions coalesce and cool, resulting in fusion. This fused metal is known as weld metal and can potentially possess different properties than the starting base metal. The weld metal can be created by the addition of filler metal or without filler metal, which is known as autogenous welding. However, autogenous welding is only possible with thin materials such as sheets or light-walled pipe and tube. Tungsten inert gas, also known as TIG, is the most common welding process that can be performed autogenously. There is no significant visual difference between an autogenous weld and a weld using filler metal other than the height of the weld bead of an autogenous weld will typically be lower because of the absence of the additional volume introduced by the filler metal. It must be realized that welding with or without filler metal cannot be used interchangeably in all instances, as it will not always produce weld metal with equivalent corrosion resistance and/or physical properties in comparison to the starting metal. As stated previously, there is no significant visual difference between the two types of weld, but there is a significant microscopic difference. As is, weld metal possesses a cast microstructure in contrast to the wrought microstructure of the starting metal. Also, solidification of the weld metal will result in segregation of alloying elements present in the weld metal. This segregation of alloying elements becomes more pronounced with stainless steels of higher alloying, which can potentially compromise the corrosion resistance of the weld metal, or the fast cooling rate of the weld metal will prevent the formation of an optimal microstructure. The potential loss of corrosion resistance can be mitigated by welding with an overalloyed filler metal. Thus, weld metal produced with an overalloyed filler metal can possess corrosion resistance equivalent to the starting base metal, while the autogenous weld metal will possess compromised corrosion resistance due to segregation of alloying elements. This table shows the chemical composition range of the important elements for corrosion resistance in stainless steel grades 304L, 316L, 2205, and superaustenitic stainless steels listed in 3A Sanitary Standard General Requirements, and the chemical composition of the respective filler metals used for TIG and MIG welding. Here we can see that the filler metal for 304L and 316L is only slightly overalloyed in chromium. These stainless steels are routinely autogenously welded and possess satisfactory corrosion resistance in service. The filler metal for 2205 is significantly overalloyed with nickel. This higher nickel content ensures that the solidified weld metal possesses the optimal duplex microstructure that is not overly ferritic, which can compromise the corrosion resistance and toughness of the weld metal. Longitudinally welded 2205 pipe, produced in accordance with ASTM A789, are autogenously welded, but are annealed after welding to restore the optimal duplex microstructure. Similarly, the filler metal for welding superaustenitic stainless steels is significantly overalloyed with molybdenum. This higher molybdenum content compensates for the significant segregation that occurs with these highly corrosion-resistant stainless steels. Otherwise, the segregation resulting from autogenous welds would significantly reduce the corrosion resistance of the weld metal. Longitudinally welded superaustenitic stainless steel pipe, produced in accordance with ASTM A312, are autogenously welded, but are annealed after welding to homogenize the composition of the weld metal and restore corrosion resistance. A defect-free weld can ensure that there are no spaces where food product can become entrapped and contaminate subsequent food production runs. And an ideal weld bead profile ensures that equipment for sanitary service can be properly cleaned after each production run. Weld defects are quite small and can be obscured by other surface features and thus are difficult to photograph. Thus, in order to describe weld defects or unacceptable features, it is common to do this with illustrations. With respect to producing welds for sanitary service, AWS D18.1 and D18.3 have identified visual examination criteria for all welds, whether they are for product contact surfaces or non-product contact surfaces. The acceptance criteria includes requirements with respect to penetration, under crevices, pits, cracks, embedded or protruding materials, concavity, and convexity. These criteria are illustrated in a number of figures in the aforementioned standards. In addition, there is a limit on the number and size of slag-like surface impurities also described within the aforementioned standards.